tau, and U vector product B is also multiplied by tau and considered at the instant t, that is the second limit of the integral. Okay. So this approximation is related to the fact that E and B vary very little, okay? But also U varies little during a collision because the electron is subjected to only to the external forces, and these external forces are not very intense, okay? So also U changes little during the collision. This is why we can take it out from the integral. Now, at this point, we take the average over all electrons, okay? So the average is a statistical average. It is not an average over time. The time is given, and it's like taking a picture of all electrons at that instant of time, and then we average all the terms that appear in the formula. So the first term on the left is the average of the velocities of the electrons at instant t. The second term is the average at instant t minus tau. Then we have on the right-hand side minus q divided by the mass. Then we have E, but E is not affected because the average is only on the electrons. So E is the same for all electrons, okay? Tau is different because each electron has a different tau. Each electron may have suffered a collision some times ago, and this time is different from one electron to another. So we must average tau. And then in the part of the integral that contains, in the part of the formula that contains B, we have that both U and tau must be averaged. So we have to average the product U times tau, okay? And of course, B is independent, so it is not averaged. Okay. Now, as you may remember from the other analysis, the average of U of t minus tau is 0. Why? Because when they suffer a collision, the collisions are randomizing. That means that after suffering a collision, the electron may have any velocity, oriented in any direction and with any value, because there is a very strong interaction with the other entity with which the electron is colliding. And this interaction cancels all possible memories of the previous motion of the electron, okay? So we can dispose of the average of U of t minus tau, and then we introduce a couple of definitions. You remember that the average velocity of the electrons, that is the statistical average of U, is called Vn. The statistical average of tau is the so-called momentum relaxation time of the electron. So we call this term tau sub Pn, in which P stands for momentum, N for electrons, okay? And then we introduce another approximation, that is the average of U tau is the product of the two averages, okay? With some approximation, this is acceptable, so that the term average of U tau can be expressed as Vn times tau Pn. So how does the original equation transform after the average. It becomes V sub n equal to minus Q mu n. We can extract tau from the parentheses. And you remember that the mobility of the electrons is defined as Q divided by the effective transport mass, average mass, times the momentum relaxation time of the electron. So this quantity is by definition the mobility, as you remember. Okay. And then we have the other factor, that is the electric field plus the average velocity of the electrons, vector product B. So simply, I mean, if we put B to 0, we recover the original expression that we already worked out in the analysis made some times ago. Okay. At this point, we remember the definition of the current density. The definition of the current density is that it is given by the product of the average velocity times the concentration of the electrons and times Q with the minus sign. There is a typo here because V should be V sub n. Okay, the sub n is missing here in two places in this formula. Okay, so we multiply by minus Qn the expression of the velocity. Obviously, the term that multiplies the electric field becomes Q mu n times n, and you remember very well that this product is the conductivity of the electrons, Q mu n times n. In the second part, it is convenient, you see, if you go up one line, you see that there is mu n multiplying B, okay? So we attach the mobility that was originally in the formula, we attach it to B, okay? If you check the units, the units of the magnetic induction happen to be just the inverse of the units of a mobility. So the product mu n B has no dimensions, it's a pure number, okay? And then we have, there is another typo, it should be QNV, not Q mu NV, okay? So there is a typo. We have QNV, okay? And of course, QNV is minus the current density. So the formula in the middle concludes with sigma n times the electric field minus Jn vector product mu nb. Okay, so this formula looks simple, but the formula is inconvenient actually, because you see that we have Jn both on the left hand side, but also on the right hand side. And Jn at the right hand side is connected with the vector product with B, so it is very inconvenient. Our purpose is to express Jn by itself, so we would like to bring Jn to the left, okay, somehow, in order to be able to express the current density as a function of the other quantities, physical quantities, okay? So we must play some trick for that, okay? So if you go one line down, you swap first the vector product. So you put B first and Jn second, so the minus sign becomes a plus, okay? So you have that Jn is equal to sigma n times the electric field plus mobility B wedge Jn. And then the trick is that we try to express the last term on the right-hand side. So this is done in the second part of the line. We take mu n b wedge Jn and we replace Jn by its own expression. Okay, so we obtain something that at first sight seems more complicated, okay, because you see that instead of Jn, we write again sigma n times E plus mobility B wedge Jn, okay? We do so because at this point in the formula, we have a double vector product. You see, we have mu n B wedge, mu n B wedge Jn, okay? Mu n is a constant, it is squared, and we should put it back later. So essentially, we have a double vector product of the form B wedge Jn. Okay, so what is the general expression of the double vector product? You can see it here. If we have any three vectors, A, B, and C, and we take the vector product of B with C, and then the result is also multiplied vectorially by A, after some calculations, we can show that the result will be the scalar product of A and C, that is a scalar quantity, times vector B, less the scalar product of A and B, which is also a scalar, times C, okay? So in the formula, we notice that A and B are equal to capital B, the magnetic field, and C is equal to the current density, okay? So if we apply this result, the double product B wedge J, J is of course Jn, we obtain the scalar product of B and J times B minus the scalar product of B by itself times J. This is little gain in general, okay, in general, but at this point we remember that the device is such that we can orient it in a way that is normal to the magnetic field, okay? So that, as you remember, the flow lines of the current are also normal to B. That means that the first scalar product here, B dot J, is 0. And B times itself is the square of the modulus, okay? So it is a scalar quantity. So because B and J are normal, actually the construction that initially looked like a more complicated expression provides a simplification, okay? So we simply replace the double vector product with minus B squared J. Then we remember that we also had the mobility squared. So the second block that appears in the expression of the current density here can be written as mu B wedge sigma E minus mu n squared B squared J, okay? And this is good because we have a scalar multiplying the current density. So that now we replace this into the original expression of the current density. So Jn is equal to sigma n times the field plus mu n b wedge sigma n e minus mu n squared b squared Jn. And we can, of course, bring this part to the left. So essentially, by this manipulation, we have been able to isolate the current density. Okay, we have Jn isolated from the rest. So we obtain the formula that you see here, this parenthesis times Jn equal to sigma. Sigma can be extracted from the remaining part of the formula times E plus mu n b wedge E. Then we divide by the coefficient of Jn. Okay, so we define a ratio between the conductance sigma n, that was the conductance associated, as you remember, to the concentration of the electrons and the mobility of the electrons. We divide by a number. This is a pure number, of course, and this number is larger than 1. So essentially, we decrease the conductance of the material by the introduction of a non-zero magnetic field. And since we are decreasing the conductance, we are increasing the resistance. Okay, so the inverse of this conductance, when the magnetic field is present, is called the magnetoresistance. Of the material. Okay, this is not the only change introduced by the presence of the magnetic field, because you see that there is also in the parenthesis here a term that is related to the presence of the magnetic field. So not only the coefficient is decreased, but we expect also that the current density will be changed as a vector, so it will also be deflected by the presence of the magnetic field. Okay, so we have two effects. One is the deflection. The flow lines of the current density will be different from the case in which the magnetic field is absent. And the coefficient multiplying the expression will also be different. We may define, just for convenience, a current that we call Jn0. That is the current that would be present if the magnetic field was absent. So if we let B equal to 0 in the formula, of course, Jn0 is simply sigma n times the electric field as we expected. Okay. So if we incorporate this definition into the formula, eventually we may write down that the true current, when the magnetic field is present, is equal to the current at zero field, at zero magnetic field, plus mu n b wedge Jn0 divided by the coefficient visible in the formula. Okay, so I will post this page after correcting the typos. Okay, and this one is connected to the other one that I was trying to show you before. So I just destroy completely this. Let me see whether I can put the other one over the screen. No way. It's nothing to do with. I don't know what happens. I'm going to destroy. All the other. Can some of you operate the mic and tell me what they see on the screen, please? Because I'm not able to. Hello?
Can see the slide.
Can you see it? Yes or no?
Yes, we can
Oh, you
see.
see. Okay, good. Sorry, because there was some confusion in the system. Okay, so now I'm trying to change the slide, taking another file. Okay, so now. Okay, you should be able to see a calculation that is similar to the calculation that I just completed a few minutes ago, just the same thing. This slide is still related to the Hall effect. So the Hall effect was examined yesterday, but I come back to it for a second because I just wanted to remind you that when we use the magnetic field as a method to measure properties using the Hall effect, the device must be elongated. So the current flows through contacts. The two contacts are on top and on the bottom, as you can see, and the current flows through contacts that are very far away. Okay, and we measure the Hall voltage through the lateral contacts that are placed in the center of the sides, and they are very small, not to interfere with the boundary conditions. Okay, so essentially the lines that you can see are the flow lines of the current. They are actually bent, okay, but they are bent only near the contacts because the contacts are far away. Okay, if instead we want to exploit the device or the material as a sensor, the geometry must be the opposite. You see, this is a sensor that exploits the magnetoresistance effect. So the sensor is very short. The two contacts are on top and on the bottom, and the distance between the two contacts is small, and the device is wide. Okay, so the bending of the flow lines of the current density is everywhere in the device. There is no position inside the device in which the flow lines are vertical, okay? So qualitatively, you understand that the current is forced to follow a path from one contact to the other that is longer with respect to the case in which there is no magnetic field, okay? So the current will change, okay, if we apply a voltage to the contacts for two reasons. One reason, as I mentioned before, is because the coefficient changes. In the bottom line of the two bottom lines of the slide, you see the definition of the symbol of the magnetoconductance, sigma NB, that is simply the ratio of the standard conductance, sigma N, divided by that number that we found out. You remember that the resistance is the inverse of the conductance, so if we just take the resistance and we divide it by the resistance when the magnetic field is absent, we obtain the ratio 1 plus mu n squared b squared. Okay. What are the applications of this? There are many, okay? Oh, this slide is just to remind you that the units, what the units of the magnetic field are, okay? So the magnetic induction, B, is measured in Tesla, okay? The equation above it is wrong. It should be B equal to mu R mu 0 H. So H is the magnetic field. And the magnetic field is measured in amperes over meter, because you see from the Maxwell equation, okay, J is ampere over square meter, and the rotational of H is the unit of H divided by a meter, okay. The absolute permeability of vacuum is mu 0. It is 4 pi 10 to the minus 7th Henry per meter. Mu sub r is the relative permeability, so it is a pure number. 1 Tesla is 10 to the 4th Gauss, or 1 Weber over square meter. So these are the units that are typically used in this field. An easy way to remember is that the mobility times the magnetic induction is a pure number. And mobility is measured in square centimeters over a volt over a second, okay? 10. We were talking about applications. There are many, of course. The magnetic field sensors are applicable for the measurement of the magnetic field of Earth, or for the reading of magnetic types of memories, okay, like disks or tapes, okay. They are also used for the recognition of magnetic in patterns in bills, for reading the credit cards, okay. And there are also more recent applications like contactless switching, or the detection of a current through the magnetic field that is around the current, okay. Or for detecting the displacements of mechanical pieces to which a magnet is attached, Okay. What are the orders of magnitude of this typical magnetic fields we were talking about? The magnetic field of Earth is the largest, okay? It's like 30 to 60 microtesla. Also, the field for the data storage is large because there is a strong proximity of the sensor to the area to be detected, okay? So data storage, reading of magnetic patterns and magnetic end of banknotes are in the same range from 10 microtesla to 10 millitesla, okay? And permanent magnets provide larger fields, like 5 to 10 millitesla for permanent magnets using switches or sensors, and even larger for magnets that are used in instrumentation. Okay, we are now going into too many details. Okay, these are typical forms of devices that are used for detection of magnetic fields. I will upload much of this material. Okay, so if any of you is interested, you can have a look at it. Okay. But I think that this is it for the magnetic sensors. So we may stop now and we shall resume in about 10 minutes. Okay, so at almost 4:40. Okay, we stop now. Okay, so we now start another subject that is related to the elastic properties of the materials in view of the analysis of the mechanical sensors. We shall see how the elastic properties of a material are connected to the microscopic properties, okay? And amazingly, it is possible to carry out an analysis that, starting from the consideration of the microscopic properties, this is the interactions among the individual atoms of the system, eventually step by step bring to the description of the macroscopic elastic properties. For the moment, we consider a system of particles that is not necessarily a crystal. Some piece of solid matter could also be amorphous, okay? And we assume that this system is made of a number of particles that may be different from each other, and that the total number of particles is some number n. Of course, this number n is in general enormous, okay? If you consider, for instance, that in a cubic centimeter of silicon, there are 5 times 10 to the 22nd atoms, okay? So a small piece of material has an enormous number of atoms in it, okay? Although in principle the description of atoms should be carried out using quantum mechanics, this type of analysis can be done using classical mechanics, okay? So we assume that these particles form a system, okay? That means that they interact with each other, okay? If there were no interaction among the particles, they would be just an individual system, each by itself, okay? So the interaction is essential for defining the system, okay? And classically, we can describe each particle using the position vector. So we shall use capital R1 to describe the position of particle number 1, capital R2, and so, up to n. And at some point, we may try to use a more compact notation. So at some point, we shall put all these vectors together in an enormous vector with many, many, many components that we shall call capital R. So obviously, this vector capital R has a number of components that is 3 times n, okay? The position of the individual particle, like the particle of index j, is some vector rj, and this vector, of course, has 3 components that we shall call x, j1, x, j2, x, j3, okay? Another important assumption is that the forces acting in the system are conservative, which means that they can be derived from a potential energy, okay? You may argue that atoms interact with each other through the electromagnetic force, okay? So the magnetic part is not really conservative. However, the velocities of the particles inside the solid piece of matter are small. And that means that the magnetic part of the force is negligible, because qualitatively one can think that the magnetic part of the force acting on a particle due to the electromagnetic field is equal to the factor V over C times the electric force, where V is the velocity of the particle and C is the speed of light. So inside the solid, the velocity of a particle is small with respect to the speed of light. So the ratio V over C is a smaller ratio, and we neglect it. In conclusion, here it is called the Hamiltonian function, but in this context, it is just the total energy. Total energy is a constant. It is equal to the kinetic energy of the atoms that we call Ta, and the potential energy of the atoms that we call Va. Obviously, the kinetic energy is the sum of the kinetic energies of the individual particles. So it is a sum of the momentum squared of particle J over twice the mass of particle J. These masses may be all different because the particles are maybe different from each other. This is the kinetic energy of particle J, and this is summed over the index from 1 to n. So the kinetic energy is always a sum of kinetic energy that are ascribed to the individual particles. So the kinetic energy is separable, okay? It is the sum of pieces that each of them belongs to one particle. Instead, the potential energy, in general, depends on all coordinates of all particles, because consider a Coulombic type of interaction, okay? That is the interaction due to the electric field between point-like particles, okay? Each particle is subjected to the interaction of all the remaining particles. So the potential energy embeds the coordinates of all particles and in general is not separable. VA in general cannot be written as the sum of pieces in which each piece contains only one or maybe a few coordinates, okay? So at this stage, the problem looks desperate, okay? It seems impossible to describe the motion of the particles unless we want to solve simultaneously an enormous set of equations that are all coupled, because the dynamics of each particle depends on the dynamics of all the remaining particles. This looks terrible, okay? However, there is a way out, and this way out is very elegant because in a piece of solid matter, the atoms are tightly bound to each other. The bonds between one atom and another atom are very strong. That means that inside a piece of solid matter, atoms actually do move, they vibrate. And the frequencies of the vibrations may also be very high, okay? But the amplitude of the vibrations is not very high. The amplitude of the vibrations is small. That means that the displacement of each atoms around some equilibrium position, they may be fast, but the elongations are not that big, okay? So atoms stay near some average position that we shall define more precisely in a second, that is the equilibrium position, okay? And this is very helpful for the analysis of the system. So you remember that in mechanics, when we have a system of particles, we define the equilibrium positions of the particle as the position that make the potential energy equal to the minimum value. So in principle, we should take the expression of the potential energy that depends on all coordinates and calculate the coordinates such that VA is in a minimum, okay? Which it is enough for us to know that this minimum does exist, okay? So the set of coordinates such that the potential energy has a minimum is called R0. R0 is the equilibrium point of the system. This does not mean that the particle sit in the equilibrium point. Okay, they vibrate around it. And we also call the value of the potential energy corresponding to the minimum, we call it VA0. Okay. Now, as I said before, the displacement of the particles with respect to the minimum is small. And this is very helpful because we can think of expanding the potential energy of the whole system in a Taylor series around the minimum. And then we truncate the expansion to second order. Okay. At that point, we obtain a simplified form of the potential energy that applies near the minimum, but of course it is correct because the particles actually do stay near the minimum. And this expression, this simplified expression of the potential energy is quadratic. Okay. Now, in order to proceed, it is preferable to change the notation because the notation otherwise has too many indices. So we change the notation for the positions. Instead of using capital X, you remember capital X11 is the component of the position of particle number 1 along the coordinate axis number 1. Okay? So we call it S1. S2 will be X12 and so on and so on. So we define a total of 3 times n coordinates S, okay? They simply describe the position, at each instant of time, the positions of the atoms using another symbol. Then we consider the displacements, that is, how much each component of the coordinates departs from the equilibrium. Okay, so given an index n that goes from 1 to 3n, so it spans over all coordinates, okay, S of n, that depends of time, less Sn0, that is a constant and corresponds to the equilibrium value of the component number n of the system. This difference is, of course, the displacement not of an atom anymore, the displacement of the nth degree of freedom of the system with respect to the equilibrium, okay? Now, these displacements are small, so we can expand the potential energy. We change the coordinates from capital X to S and then from S to psi. And we also note that since we start the expansion, in the series expansion from a minimum, the first order derivatives are 0 because we start in the minimum, okay? So in the Taylor expansion, we expect to have the 0 order term, that is the minimum, the value of the potential energy in the minimum. Then we do not have any first order term, and then we have the second order term. So you see the expansion here at the bottom. The potential energy in the new coordinates, and after performing the second order expansion, becomes VA0, that is its value in the minimum, as we noticed before, plus the second order term. And the second order term, of course, is 1/2 times a double sum with some coefficients times the displacements of the two indices. So we have a double sum over two different indices. Each index runs from 1 to 3n independently from each other. Psi k is the displacement associated to k, psi n is associated to n, and the coefficients obviously are the second derivative of the potential energy with respect to psi k and psi n, calculated in the minimum, that is in the position where the displacements are 0. Okay, so this is the second order expansion in which the coefficients c, k, n have two indices. And both indices go from 1 to 3n. So the total set of coefficients c, k, n is a matrix, a square matrix. And this square matrix is of order 3n, okay, which is enormous, obviously, okay? Again, if you consider a cubic centimeter of silicon, you have 5 times 10 to the 22nd atoms to be multiplied by 3, because you have 3 components for the positions of each atom, or each atom. It is also interesting to state some properties of this matrix. First of all, this matrix is obviously symmetric, because if you exchange the two indices, this simply means that you are performing the derivative you derive first with respect to k and then to n, psi k, psi n. Or if you exchange the indices, you derive first with respect to psi n and then to psi k, but of course this is irrelevant. So this matrix is symmetric. But there is also another important property to this matrix, because since we started the expansion from the minimum, that means that VA0 is the minimum of VA, okay? So VA in a position different from the minimum, so this formula is obviously larger than VA0 by construction, okay? That means that this double sum is strictly positive for any choice of the displacement. It doesn't really matter where you select the displacement, okay? As long as this formula applies, this double sum is strictly positive, no matter what the individual values of the displacements are, okay? But you remember, this is due to a property of the matrix. So this matrix, it is not only symmetric, but also positive definite, okay? So these are two very important properties of this matrix that will allow us to make a lot of calculations that make the analysis much easier. So the matrix is symmetric and positive definite. By the way, this matrix is called the elastic matrix, okay? And I am sure that you have met before the one-dimensional counterpart of the elastic matrix. If you think of a one-dimensional problem, you have only one index. If you take a one-dimensional problem, one-dimensional means that you have only one atom, and this atom can move only along one axis, like the x-axis, okay? So in that case, if you have only one index, psi k will be equal to psi n. So you will have, instead of the sum, you will have a single term, 1/2 c psi squared. And if the potential energy is 1/2 c psi squared, then the force, you remember, the force is minus the derivative of the potential energy with respect to x. So in the one-dimensional version of this formula, the force will be minus c times psi. So it will be exactly the force that is of the elastic type, proportional to the elongation with respect to the origin. So this formula generalizes to many dimensions the elastic force typical of some one-dimensional problem, like the mass connected to the origin with a spring, or the pendulum, all these things, okay? What happens if we want to calculate the force in this more general situation? Well, we can always remember that due to the definition of the potential energy, if we take, you see it here, the derivative of the potential energy in the general case, okay, without any Taylor expansion, with respect to 1 capital X jk with the minus. You remember, J counts the atom, K counts the axis. So this is the force that acts on atom number J in the direction of the axis of index K, let's say X direction 1, 2, or 3, okay? In the new symbols, we are using only one index, okay, but the conclusion is the same. The force, the component of the force associated to some index R, is the derivative of the potential energy with respect to that index. And if you use the quadratic expression that comes from the Taylor expansion, obviously the force, being the derivative of a quadratic expression, will be linear with the minus, okay? So this force is minus the sum of this elastic coefficient times the displacement. You remember that in mechanics, if you have a one-dimensional problem in which the force is proportional to the displacement with a minus sign, the result of the dynamics is that the mass oscillates to and fro, okay? And that is called the linear harmonic oscillator, okay? This is a generalization of that problem. We have a force that is a linear combination of the displacement, of all displacement. So it looks like being a linear, the problem seems to be a linear combination of linear harmonic oscillators, okay? Now, what is the next issue? The next issue is the following. You remember we started with a general form of the total energy. We understood that the kinetic part is the sum of individual pieces, so it is separable, okay? Whereas the potential part is a mixture of all coordinates, so it is non-separable in general, okay? Now we have a simpler expression of the potential energy. We may ask ourselves, is it separable? Well, no. You see, you have the products of different coordinates, okay? It is not yet separable, but we may try to do something to make it separable. So the rest of the analysis for today will be devoted to understanding how to separate this problem, so that after separation, we can analyze the motion of each individual degree of freedom separately from all the rest of the system, okay? To do so, it is better to introduce a matrix and vector notation. So we call with symbol capital C, this one, the elastic matrix, okay? So this is a gigantic matrix of order 3n by 3n. And then we also introduce a column vector whose elements are the displacements, okay? So if we want to express the potential energy after the expansion to the second order in vector form, we may do this. We may write the second order expansion as the vector of the displacement that is pre-multiplied by the matrix. So C times psi is again a column vector, okay? And then we multiply by the transpose of psi, okay? If you do that, you find exactly the second order expression, the quadratic expression that we had before. Now what we want to do to continue is to express also the kinetic part of the energy in vector form. This is relatively easy because you see in the kinetic part, we have an expression that is already separated, and we have the masses as coefficients. So what we can do is, first of all, in a conservative problem and in Cartesian coordinates, capital P, that is the momentum of the particle, is equal to the mass times the velocity. So the kinetic energy can be written as, you see in the next of this formula here, P becomes m times the velocity. So we have the mass squared divided by the mass, that gives you this, times the square of the velocity, and the velocity of the individual particle is just the sum of the derivatives with respect to time of the three components squared. Okay, so this expression can immediately be set up in matrix form. Of course, we have to introduce the new components that we call psi. Okay, so x dot becomes psi dot. Then we introduce the matrix whose elements are over the diagonal are the masses of the particles. Okay, so you remember the first three components are related to particle 1 and axis 1, 2, and 3. So of course the mass is the same. So we have M1 3 times. Then we continue along the diagonal and we end up with Mn 3 times, and all the remaining entries of this matrix are 0. So this is the mass matrix that is a diagonal matrix. So in summary, the total energy takes the form that you can see here, 1/2 psi dot transpose times m times psi dot plus 1/2 psi transpose times C, that is the elastic matrix, times psi, and then we have the minimum of the potential energy that is simply an additive constant. Okay? Now, the mathematical problem is this. You see that you have that apart from the constant at the right-hand side, the total energy is the sum of two quadratic forms. One quadratic form is the kinetic part of the total energy, and this quadratic form is already diagonal because matrix M is diagonal. On the other hand, the quadratic form associated to the potential energy is not separated, is not diagonal, because the matrix, the elastic matrix C, is actually full. Okay? So at this point, you must remember some procedure that you have met in some class of algebra. When you have a matrix, and this matrix is symmetric, then the eigenvalues of the matrix are real. And that also means that the eigenvectors can always be taken as real. This is property number 1. Property number 2 is that besides being symmetric, the matrix, the elastic matrix C, is also positive definite. That means that the eigenvalues, besides being real, are also positive. Okay? This matrix is easy to deal with because if you have a matrix that has positive and real and positive eigenvalues, you can always find a rotation of the frame. When you introduce a rotation of the frame, you will rotate everything, okay? You rotate the vectors, matrices, etc., okay? In order to transform the original quadratic form in a form that is diagonal, in which the new matrix is diagonal. This can always be done with a real transformation if you have a matrix that is real and positive definite, symmetric and positive definite. Okay? Where is the difficulty? The difficulty is that if you rotate the matrix of the potential energy, what you do is you introduce a change in the vector psi, okay? You apply a linear transformation in the vector psi. And this linear transformation transforms C into a diagonal matrix. But then you do the same thing in the kinetic energy, because if you transform psi, you must transform psi everywhere. So if you transform psi in the expression of the kinetic energy, there is a danger that the transformation will transform M, that is already diagonal, into something that is non-diagonal anymore. Okay, so you clean the potential energy, but you risk to destroy the kinetic energy, in the sense that the final form may not be diagonal anymore. Okay, so the issue is to find a transformation that makes C diagonal, that transforms C into something else that is diagonal, and leaves M, or transforms M, into something else that is still diagonal. Okay? And this transformation does exist, and it is related to a solution of an eigenvalue equation. So the eigenvalue equation is visible in the middle of the page. This is a special type of eigenvalue equation, because assume for a moment that M is not there, okay, that the equation is C times eta sigma equal to lambda sigma eta sigma, okay? This would be a pure eigenvalue equation associated to matrix C, with lambda the eigenvalue and eta the eigenvector. Instead, we must solve a modified eigenvalue equation in which not only C but also M enter the equation. Okay, so the modified eigenvalue equation to be solved has the form that is visible in the middle of the page. It is C times eta sigma. Eta sigma is the eigenvector of index sigma, equal to the eigenvalue lambda sigma times M multiplied by eta sigma. How many eigenvalues do we expect? Well, you remember that when you solve an eigenvalue equation derived in this form, you reduce it to an algebraic system, an algebraic equation of order equal to the order of the matrix. So the matrix is of order 3n. The degree of the algebraic equation to be solved is also of order 3n, which is, of course, terrible. And an algebraic equation of order 3n has 3n solutions. Okay, so the possible eigenvalues lambda sigma are in total 3n. They may not be different from each other in some cases, but the total number, including the multiplicity, is 3n. And to each eigenvalue, we associate an eigenvector, okay? The issue is all these numbers, lambda, are real and they are also positive, okay? So we can always take the eigenvectors eta as real as well. You remember from algebra that we can always select the eigenvectors so that they are mutually orthogonal. We shall see it in a second, okay? Then the eigenvectors will be linearly independent. And finally, consider that the eigenvalue equation is homogeneous. The eigenvectors are defined apart from a multiplicative constant. So, due to the special form of the eigenvalue equation, the orthogonality condition that we impose to the eigenvectors will also be special. And it has the form that is on the last line. That means that if we take any eigenvector eta with index tau, multiply it by m, then multiply the result by the transpose of eta of index sigma. If the two indices are equal, that is, if you are using twice the same eigenvector in this calculation, the result will be 1. If the two indices are different, so if you are taking different eigenvectors, the result will be 0. This is also expressed by saying that the eigenvectors are mutually orthogonal with respect to matrix M. Okay, this is a generalization to the concept of orthogonality of vectors. Okay, so we write this in a compact form: eta sigma transpose times M times eta tau is equal to the Kronecker delta of sigma and tau. Okay. What is the difficult part of all of it? Because conceptually, it is quite easy, okay? We just state definitions and property. The actual practical difficulty is to solve the eigenvalue equation, because this eigenvalue provides a system that is of an order that is enormous, okay? We shall see that in a crystal, this equation simplifies very much, and this is thanks to the periodicity of the crystal. Okay, so the difficulty of solving this equation here is enormous in a general case, but in a crystal, due to periodicity, it becomes relatively easy. For the moment, we assume that somebody has solved this equation so that we know all eigenvalues lambda and all eigenvectors eta, and we also know that all these eigenvectors are mutually independent. Okay. Okay, considering that we assume that the eigenvectors have been found, we arrange them in a matrix form. So we take eigenvector of index 1, okay? So this eigenvector will have one component eta 1, 1. The second component will be eta 1, 2, and we go down. The last component will be eta 1, 3n. So the first index in this matrix counts the eigenvector, and the second index counts the component. So the first column is made of the first eigenvector. The second column is the second eigenvectors. The last column is the last eigenvectors. You remember, by the way, we call it G. G is the matrix made of the eigenvectors. Of course, you remember, all these eigenvectors are linearly independent. It follows that all the columns of this matrix are linearly independent. That means that the matrix is non-singular. And if the matrix is non-singular, there is the inverse. The inverse of G does exist. Okay? So, given that, we can rewrite the condition of orthogonality, this one, in matrix form, because we can write this expression using sigma equal to 1 and t equal tau equal to 1. Then we rewrite it for another pair of indices, and so on and so on. And we put all these expressions together. Okay, you remember eta is one of the possible columns of the big matrix G, and same for the other eta here. So this condition of orthogonality with respect to M can be written in matrix form like here. Okay, it is the transpose of GT times M times G is equal to I. I is the identity matrix. It is the matrix in which the diagonal is made of ones, and all the remaining part of the matrix is made of zeros. Okay, so this is the fundamental relation that allows us to diagonalize the total energy of the system of particles. From this expression, before just, we have 2 minutes before the intermission, with this expression we can deduce other useful expressions. For instance, consider the original equality and multiply to the right both sides by the inverse of G. So I times the inverse of G, of course, gives you the inverse of G, because this is the identity. Here you have G times the inverse of G, that gives you the identity that is not written. Okay, so this expression here is obtained immediately by multiplying to the right the original expression by the inverse of G. Then you take the result here and multiply the result to the left by G. So GTM, putting a G on the left, gives you GTM. G times the inverse gives you the identity. Again, we start over from the original expression and we multiply to the left by the inverse transpose, that is GT minus 1. So I times GT minus 1 gives you GT minus 1. GT minus 1 times GT gives you identity. And finally, we multiply by GT to the right this expression here, and we obtain mg/gt equal to identity. So we have 5 expressions that will be useful for diagonalizing the total energy of the system. Okay, so we stop now for 10 minutes and we will complete in the next hour. the identity here, here, in other locations. And then we use for the identity one of the expressions where there is the identity. Okay, so it is this type of replacement. Before we do that, we also place the eigenvalues in a diagonal form. So we define a diagonal matrix that is such that the diagonal is made of the eigenvalues and all the remaining non-diagonal terms are equal to 0. So after defining the matrix of the eigenvalues, we can write the original eigenvalue matrix, eigenvalue equation, sorry, in another form. Instead of eta, we place G here and there. And instead of lambda, we use the matrix of the eigenvalue. So we simply obtain a more general form of the same equation. So the equation, the eigenvalue equation in full matrix form is this. Instead of eta, we have the set of all etas. Same here, and instead of the eigenvalues, we have the matrix of the eigenvalues. Then we start by multiplying to the left the eigenvalue equation by the transpose of G. Okay? When we do so, at the right-hand side, we have GTMG that, because of one of the other relations that we found before, is the identity. So by this manipulation, we have found that GT chi G is equal to L, is diagonal. And now we start doing the operations that I anticipated. Assume that between the transpose of psi and C, we insert the identity that, of course, changes nothing, okay? And then we replace the identity with mg transpose, because from the previous page, we remember that mg transpose is identity, okay? Then again, between C and psi, we imagine that there is the identity, and in this case, we use G transpose M, because this is also the identity. Then you remember that when we have products of matrices, we can associate them as we like, okay? That means that we can change the position of the parentheses in this formula. So we simply regroup. We do not change the order of the terms, of course, but we regroup them so that we have psi transpose mg form the first group. You see it's here, there, and there. Then we have G transpose CG here. But this is equal to L, it's diagonal. And then we have GTM psi. Okay. So this is the first step. The quantity, the parenthesis in the middle is L because of this expression. So this has become diagonal. Okay. What about the rest, all the quantities that are in parentheses? So now we introduce some other definition. We take psi is a vector, and G minus 1 is the inverse of G, that is a matrix, okay? So G minus 1 times G is a linear transformation on psi. So that simply it gives, from the original vector psi, it gives you another vector that we call B, okay? But then we remember from the other relations that G minus 1 is GTM. So we replace it here. On the other hand, obviously, if B is equal to psi times the inverse of G, this is also can also be written as psi equal to GB. We simply multiply by G both terms of this, okay? When we take the transpose of a product of matrices or vector, you remember the transpose is obtained by taking the transpose factors in the inverse order. So the transpose of psi is B transpose that comes first, followed by G transpose, okay? Then we start coming to the conclusion because psi transpose mg, because of this expression, you remember we must clean up these parentheses and this parenthesis. So psi transpose mg, that is the first parenthesis. Psi transpose is B transpose times G transpose. And G transpose mg is the identity, remember. So this is B transpose. So all these parentheses has become B transpose. Okay. And due to this, we have that the second parenthesis, G transpose M psi, is B due to this. Conclusion, if you go through all these chain of equalities, you find that apart the factor 1/2, this, you remember, is the quadratic part of the potential energy that is non-diagonal. It transforms into this, and this is diagonal because L is the matrix of the eigenvalues, as such a matrix is diagonal. So we have indeed found a linear transformation on the unknown vector psi, such that using the new unknown vector B, the expression of the potential energy is diagonal. Now the issue is, what happened to the kinetic energy? Well, the kinetic energy stays diagonal because this is the expression of the kinetic energy matrix form. Derivative with respect to time of the displacement times the mass times the derivative again, okay? Now, psi t dot is, if you take the time derivative of this, G is independent of time, of course. So we get bt dot. And psi dot is like GB dot, and in the middle we have GTMG, that is identity. So not only the kinetic part of the total energy stays diagonal after the transformation from psi to B, but it is even simpler because we have the identity here instead of the masses. Okay? So conclusion, we have successfully made the total energy diagonal. So in the new variables are the quantities that form the vector B. And they are related to the actual displacements by this definition here, or this definition here. So if we succeed in calculating B, then by simply multiplying by G, we obtain the actual displacements of the atoms. Okay, so the issue is to calculate B, each component of vector B. So in the new variables, we find that the kinetic energy is 1/2 B dot transpose B dot, that is diagonal. The potential energy is 1/2 B transpose LB plus the constant. Okay. Before we continue, we ask ourselves, what are the units of L? L is a matrix whose diagonal is made of the eigenvalues. Okay, and you see immediately that this form BTLB must be homogeneous with this form. They must have the same units because they are in the same formula. Here we have B dot B dot. So the units of these are the square of the units of B divided by a time squared, because we have B dot and B dot, and the derivative is like dividing by the time. In conclusion, L must have the units of the inverse of a time squared. Then we also know that the elements of L are the eigenvalues lambda, and these eigenvalues are all positive, real and positive, because the matrix is symmetric and positive definite. So we have a set of positive quantities whose units are those of the inverse of a square time. So it is sensible to call them omega squared. Omega is an angular frequency. Okay, so instead of writing lambda of sigma, we write omega squared of sigma. Now, what is the expression of B dot T B dot? Is just the sum of individual elements B dot sigma squared. Okay. So it is the sum of individual elements depending on index sigma. Also, the potential part of the energy is equal to the sum of elements whose form is 1/2 omega squared sigma B squared sigma. Okay, so we can call this expression H sub S. It is the total energy associated to, sorry, of index sigma, not S, is the total energy associated to the single degree of freedom of the system, and the total energy, apart from the constant VA0, can be written as the sum of these quantities. So, in conclusion, we have completely separated the system. The system has a total energy that is written as the sum of individual pieces. Each piece is called capital H sigma, and it is associated to one and only one degree of freedom of the system. Okay? If we solve this individual component or degree of freedom, okay, we find that, I mean, each individual piece is equal to a constant, okay, because the total energy of the system is the sum of the energies of each individual system. And since the individual systems are separated from each other, the individual degrees of freedom in this representation are separated, they do not exchange energy from each other. Each individual system is associated only to its own index, with its own velocity b dot and its own displacement or position b. Okay, so there is no exchange of energy from one degree of freedom to the other in this representation. That means that since the total energy of the atoms is conserved, because the total energy the system is conservative, also the individual degrees of freedom are conservative. That means that the individual energy associated to index system is some constant. And the total energy of the system is the sum of all these constants plus the minimum VA0 of the potential energy. If one solves the system, I don't know how much you remember of Hamiltonian mechanics, but if you consider the total energy here as the Hamiltonian function of the individual degree of freedom, you will remember that the derivative of the Hamiltonian with respect to the coordinate is minus the derivative of momentum, that is minus the force. And the derivative of the Hamiltonian with respect to the momentum is equal to the velocity of the degree of freedom, okay? So if you combine these notions that are elementary Hamiltonian mechanics, you eventually find that the equation fulfilled by the individual degree of freedom B is of this type. It's second derivative of B equal to minus a positive constant times B itself. So you remember very well that this is the equation of the so-called linear harmonic oscillator. The solution of this differential equation is some constant times the cosine of omega t plus a phase, okay? So the individual degree of freedom B, after the separation of the variables, behaves like a linear harmonic oscillator. This does not mean that the atoms are linear harmonic oscillators. This means that after solving this in these new variables, one has to go back and find the displacements psi by multiplying the individual degrees of freedom by matrix G. So eventually, the actual displacements of the atoms are a complicated combination of linear harmonic oscillators, okay? Only in the separated coordinates, each degree of freedom acts as a single linear harmonic oscillator. Conclusion. each B behaves in time like this, it may be convenient to use the complex notation. So instead of the cosine, using complex exponentials. Omega sigma, of course, is the angular frequency of the oscillations. And the quantities that we have just found, that is B of sigma, as you may well remember, are called the normal coordinates of the system, or also they are called the principal coordinates of the system. Also, the oscillation of the normal coordinate of index sigma is also called the mode of the vibrating system. So you may think of this set of many, many atoms that vibrate around the equilibrium positions, and we have just decomposed the motions of the atoms that are very complex in a superposition of oscillatory motions that are called modes or vibrational modes of the materials. Okay. As I said before, after calculating the B quantities, one calculates the actual displacements, and from them you may also calculate the actual positions S of the atoms. Obviously, in order to fully calculate these quantities, since we started from an equation, a differential equation of the second order with respect to time, it is necessary that we know the initial position and the initial velocity of each degree of freedom of the system, which is, of course, something that in practice is impossible, because not only because of the numbers, but also because of quantum mechanics that forbids this. Okay, but in any case, this description is very, very useful for several reasons. And one reason is that after the calculation that we have done is completed, and you remember this calculation has been done only fully in the classical mechanics environment, okay? We never introduce any quantum mechanics. But when we have reached this point, it is relatively easy. We are not doing it now, okay? It is relatively easy to quantize the system, because the quantization of the linear harmonic oscillator is a very well-known problem of quantum mechanics, okay? So we simply go from classical to quantum in one step, okay, if we wish. This is something that we already mentioned. This is the total energy less the value at the minimum is separable. The total energy is conserved because each degree of freedom in the normal coordinates keeps the energy. Where is the real difficulty of the problem? The real difficulty is to solve the eigenvalue equation. That is, to solve the equation that is here in the bottom line of the page, okay? We did not solve it. We said somebody has solved the equation for us and found the set of eigenvalues and eigenvectors, okay? The problem is really complicated if we have a general system made of many, many atoms, okay? Instead, the problem becomes considerably easier if we deal with a periodic structure, the system becomes quite easy, okay? So for the periodic structure, and the crystals are periodic, we have the possibility to continue the analysis. Of course, today it is very late, so we shall do very little, but let me proceed in order just to introduce what comes next. We neglect this part because it is quantum. Okay, so we are here, and this replicates exactly the line that was visible in the other page. Okay, we have an eigenvalue to solve. The matrix C is the elastic matrix, so it is the same, made of the second derivative, so the potential energy with respect to the coordinates, calculated at the equilibrium point. And the matrix M is the matrix of the masses, is a diagonal matrix in which we have the masses here are indicated with the symbol mu. Mu of K is the mass associated to the kth degree of freedom. Okay. Now we assume that the system that we are considering is a crystal, that is a periodic structure. Okay, you remember that we introduced some concepts in the crystal. Okay, we introduced, for instance, the concept of elementary cell. Okay, and we said a crystal is made of a number of elementary, these are the elementary cells of the direct lattice. Okay. The cells are equal to each other. They cover completely the crystal, and assume that the number of cell is some NC. Okay. You also remember that we have called basis. Basis is a group of atoms that replicates itself periodically. So inside of one elementary cell, we have either one atom or a group of atoms that constitutes the basis. Okay. So assume that the basis is made of a number of nuclei that is NB. This number NB is small, like 2 or 3. It's not a very big number, okay? So if we have NC elementary cells, and inside each elementary cells we have NB nuclei, the total number of nuclei is N, equal, of course, to the product NB times NC, and each atom has 3 degrees of freedom, so we have a system that is made of 3n degrees of freedom. Again, it is very, very, very large, okay? So, but we shall see that due to periodicity, we can very strongly simplify the problem. Now there is a technical difficulty. Okay. To proceed, we must be able to identify each individual cell of the crystal. Then, inside each individual cell, we must be able to identify the different atoms that form the basis. And for each atom of the basis, we must be able to identify the equilibrium position and the displacement. Okay, so the technical difficulty is that now we have to quit on the very convenient method of having one index. You remember we numbered all the degrees of freedom with one index. We cannot do it anymore. We must distinguish indices for the cells, indices for the equilibrium position of the atoms inside the cells, and indices for the displacements. Okay, so the notation will become much worse for a while, but eventually we shall slowly recover an easier notation. Okay, so we start by identifying the cells. Remember, we introduced in the original discussion about the lattices, we introduced the translational vector that goes from the node arbitrarily selected as origin to the node identifying the cell of the direct lattice. Okay, so we introduce these translational vectors. Any general translational vector here is called L sub m. Okay, m is the counter of the cell. Okay, so this vector points from the general origin of the coordinates to the local origin, that is the center, the node of the mth cell. So this node is the local origin inside the cell. Then the positions, the equilibrium positions of the nuclei belonging to this cell will be identified by another vector that we call rho alpha. So rho alpha is a vector that, starting from the node of the mth cell, joins this node with the equilibrium position of the nucleus of index alpha. Remember, in the node identified by LM, it is not necessary that we have any atom, okay? It's just a point of the cell, okay? So index M goes from 1 to NC because it is the counter of the cells. Index alpha, it is also an integer, goes from 1 to NB because it is the counter of the atoms of the basis inside the individual cell. Okay? And finally, we must distinguish the components along each coordinate axis, 1, 2, or 3. Okay, so in conclusion, we must use for a while 3 indices. One index is M. As I said before, it goes from 1 to NC. The second index is alpha. It goes from 1 to NB. And the third index is U. It is either 1, 2, or 3. Okay? So a displacement, instead of being indicated with psi q, with only one index, would be indicated as psi m alpha u. That is the displacement along axis u of atom alpha of cell M. And if we have two of them, we need two sets of indices, okay? Because you remember we have quadratic expressions with psi q and psi r, for instance. This is a two-dimensional picture that shows, let me make it smaller. So the one on the bottom left is the cell containing the origin. The center of another cell is identified by L. So if this cell is cell number n, this vector will be Ln. There is no need of having an atom in this point. It's just the center of the cell. This other cell has the index m, so this is Lm. Then the equilibrium position of the atom of index alpha inside this cell is rho alpha, but it is not necessary that this atom is in the equilibrium position. It could be anywhere around it, okay? So assume that this atom is here, okay? So this small vector is the displacement with respect to the position indicated by rho alpha, with two components, because we are in a two-dimensional picture, okay? So this psi is the horizontal and this other psi is the vertical, okay? Instead, you remember symbol S. Symbol S initially designated the actual position of the atom with respect to the origin, okay? So S is with respect to the origin. Psi is with respect to the local reference. How does the notation change because of these many indices? Okay. When we consider the elastic matrix has two indices, so it must become 6. Okay, so we place them, 3 of them on the bottom and 3 of them on top. Okay, and the meaning is, as you can see on the right, this one. So one of the psi provides the indices on the bottom and the other the indices on top. Obviously, since the elastic matrix is symmetric, we can swap the indices. So if we rigidly take the lower indices and put them on top, and then we take the upper indices and put them to the bottom, it is the same. Okay. Then we remember that the crystal, as long as the crystal is infinite, the crystal is periodic. In principle, a finite crystal is not periodic, but we can recover, you remember, the periodicity with the trick of imposing the periodic boundary conditions, okay? So again, we can think that the lattice is periodic, okay? This is a very important point, because if the crystal is periodic, we can demonstrate the first property of the entries of the elastic matrix. These entries are invariant under translation. That means that if we move from one cell to another, okay, this will not introduce variations in the components of the elastic matrix. Why? Well, assume that we impose a translation to the indices, okay? So that the index that, sorry, the translational vector that identifies this cell M is replaced with Lm plus Lni, with any translation Ni, okay? And the same another index, Ln, is given the same translation, okay? What does it mean? It means that you see in the elastic matrix, we have the same time M and N, okay? So we shift at the same time by the same vector the positions of the cell without changing the other indices, beta, alpha, W, and U, okay? Then we take a special form of the translation. We take the negative translation of Ln, okay? That means that Ln becomes 0. Lm becomes, as you can see here, Lm minus Ln, okay? So the conclusion is that physically, we can state that, you remember the meaning of the elastic coefficients is that they define the force that applies on some degree of freedom of the crystal, okay? If you consider C of M and N, you are considering the force that applies on an atom placed in cell number M due to the action of another atom that belongs to cell number N, okay? Now, it is intuitive that this action must depend only on the relative positions of the two cells, not on their absolute positions, okay? Because the force that is acting between two atoms cannot depend on the choice of the origin of the reference, and inserting a translation is like shifting the reference, okay? So the force depends only on the relative distance, not on the absolute position of the atoms, okay? So we can conclude that as far as the indices of the cells are concerned, the elements of the elastic matrix depend only on the distance between the two cells involved, not on the absolute positions. Now, of course, we consider that all the other indices are fixed. That is alpha and beta, that are the pointers to the atoms with respect to the local reference, and the U and W indices that are the are related to the coordinate axis, okay? Now, if you now consider again the indices m and n, what are the possible distinct differences between them? Well, one is 0. M minus n can be 0 if they are taken equal. Then you have m minus n equal to 1. N minus n equal to nc minus 1. Okay? But if you continue, you see that all possible combinations of distances of the indices m and n can only give you these possibilities that are indicated in this line. That is, the number of possible distinct entries of C, will related to the indices m and n, are only nc. The total number of distinct entries of C with respect to these indices is nc, not nc squared, as one would expect, because we have a matrix of this form. Okay? Why? Because if you try to consider all other possible distances between the nodes, you find immediately that due to the periodicity of the crystals, all the other possible distances replicate themselves. Okay? So you must appreciate this, because we are reducing enormously the number of degrees of freedom of the system due to the periodicity. Another issue that is also obvious is that the mass of an atom of the base cannot depend on the index of the cell, okay? If at each position in the cell we have the same atom because they are periodically replicating themselves, the masses are the same. And of course, the masses cannot either depend on the axis, on the coordinate axis, okay? So we can also simplify the mass matrix, because in principle, the mass matrix has all these indices, okay? But obviously, mass cannot depend on the cell, so we drop index n, and we also drop the index of the axis, okay? The mass can only depend on the index of the vector of the local reference, so it can only depend on rho alpha. So if this atom is different from this atom and different from this atom, the three masses are different. But this atom here is equal to this, and to this, and to this, and so on. So it does not depend on the index of the cell, and of course it does not depend on the index of the axis. Okay, so we now finish, but the message is periodicity will decrease enormously the number of degrees of freedom of the system, to the point that it actually becomes solvable in a relatively easy way. Okay, so we stop and we shall continue on Tuesday. Thank you.